interacting with us. So with that said, we can start our first poll here. So let me launch my first slide. And so the poll question is, since this is a lunch and learn without a lunch, what is the best smoked meat? A, okay. Yeah, so he opened the poll. So what's the best smoked meat? Is it pork shoulder shredded, pork shoulder sliced, brisket, pork ribs with a dry rub, or other? And this is probably the most important poll that we'll have. Okay, it looks like, oh wow, look at that. Brisket and pork ribs with a dry rub are tied neck and neck. Oh, well, it's all over the place. Pork shoulder shredded is surpassing. Okay, we'll close the poll. Looks like pork shoulder shredded just barely beat out brisket. We must not have any Texans here today. Okay, on a more serious note, let's continue on with our presentation. And what I wanted to do today was talk about electrical protection of your motor. Now, what I talked about, I think it was last Wednesday, or whenever I last spoke to you guys on John's Lunch and Learns like this, we talked about the motor thermal model. Very important there. But beyond the thermal model, we also have to have electrical protection in the motor so that if the stator insulation fails or other things fail, we protect that motor and we remove a fault or some other abnormal condition. So I'm always fond of saying that machines on the power system have to have protection not only from short circuit conditions, but they also have to have protection from some abnormal operating conditions. Now, certainly, a short circuit is an abnormal operating condition, but when I think about these abnormal operating conditions, I think about things like undervoltage, overvoltage, unbalanced current, things like that. And we'll talk about those. Now, machines on the power system that are affected by these abnormal conditions, that includes motors, generators, and transformers. Well, you've got to protect all of these things for these abnormal operating conditions. But first of these we'll talk about is an overvoltage. Now, when we overvoltage any machine, we will also overexcite the machine. So if we overexcite the machine, excitation is given by volts per hertz. So because we're increasing the voltage, we're going to overexcite the machine, and we're going to drive excitation currents in places that they're not meant to be, like the motor frame or the transformer frame, things like that. So we need to protect for that reason. The other thing that we might do is we probably are going to decrease the load current. So we're going to have less load, and we're probably going to affect the power factor. Now, most of these things that damage for overvoltage like this, they will cause, especially the overexcitation, they will cause damage by heat, and it takes a while for heat to start causing problems, or for that heat to be generated. So typically, the overvoltage protection can be set with a fairly long time delay. And you want to set this with a fairly long time delay so that you don't misoperate for just abnormal system conditions, right? So, that are very transient in nature. But typically, you're going to set the overvoltage to around 110% of nameplate voltage. And the reason for that is the motor probably is rated for a 10% overexcitation. So as long as you've got nominal frequency there, you can protect for that 10% overexcitation by setting at 110% voltage. Another protection function that you might want to do is if you have a gross overvoltage, you may actually break down the insulation of the motor because of that gross overvoltage. Now, this is an overvoltage by 20, 30, 40%. These are rare in the power system. you very seldom have to worry about this sort of condition unless you're at a generating station where you might be syncing up the generator or something like that and cause an overvoltage condition. If that's the case, then you may want to set a gross overvoltage element with a very short time delay. But typically you set it 110% of nameplate with a fairly long time delay. Okay. Undervoltage, we might want to use undervoltage protection also. Now, undervoltage or undervoltage condition causes problems on the motor in the same way, sort of, that an overvoltage does, in that it causes a heat problem. Now, the reason it causes a heat problem is because when you have an undervoltage condition, that motor wants to be a constant power device. So it wants to keep a constant power on the shaft of the motor. And so when you undervoltage, it means you're going to draw more current. And that more current is going to manifest itself as additional heating, more I2R losses. Now, those, since you're drawing more current, that additional heating will be rolled into the motor thermal model, but you may still want to trip for this undervoltage element also. So it sort of serves as a backup protection for the motor thermal model, mainly because it can be set to trip faster than the thermal overload. So typically, you can set this to about 90% of nameplate. Now, on this particular element, undervoltage protection should be used with caution. And the reason I say that is because undervoltage element can misoperate. If you have a system condition, let's say you've got a really large motor that's starting, that's adjacent to the motor that you're protecting, and that motor drags down the bus voltage to 80%. That's less than this 90% that you're setting this. So you have to say, if you're going to use undervoltage, then you should set that with a long enough time delay so that you don't misoperate or system faults that are elsewhere in your system that would also cause a voltage collapse. But also, you need to set it with a long enough time delay so that you can start those large motors that are going to drag down your bus voltage. So these typically are set with a fairly long time delay. So if you've got a motor a big ID fan that takes 15 seconds to start, then you need to coordinate that time delay with we need to coordinate the undervoltage time delay with that big ID fan. So it may take 15 seconds. Now that's an eternity in the protection world, but still, it's a backup to the thermal overload element, which might take, minutes to operate for that same undervoltage condition. Okay. So typically you don't operate from harmonics, right? So I might not trip from harmonics, but I might want to alarm on harmonics. Now, harmonics can tell us some certain things. They can help us diagnose problems inside the power system. So we can raise an alarm based on that harmonic content. So if we've got a drive that's having a particular problem, or if the drive is injecting some noise onto our power system, we can look at the harmonic current or the harmonic voltage that's on our power system and raise an alarm for that. So most of the time, the way that we would typically do a harmonic alarm is we could set a harmonic detection function that's available in the 869. We can set that to a particular harmonic, or we can set it to THD. And THD stands for total harmonic distortion. And so that's the level of all the harmonics that the relay can calculate. Now, 869 can go up to about the 25th harmonic or so. So it can certainly capture nearly everything that you need. Okay, so now let's talk about some of the other electrical protection functions. Now, when I talked about the motor thermal model, I mentioned that we would typically set a K factor that would bias the motor thermal model based on the amount of unbalanced current. Now, this is very important because if you had loose conditions, you had upstream blown fuses, things of that nature, that unbalanced voltage, which would manifest itself then as unbalanced current into the motor, it produces extra rotor heating. Extra rotor heating that is at twice the system frequency. So there's a lot of skin effect in that on the rotor because of the higher frequency. It causes a lot of extra heating. So we certainly want to bias the motor thermal model for that. But if we do have a gross unbalance, something like a blown fuse, or we're single phasing the motor, there's no need to wait for the motor thermal model to model that extra heating and trip based on that. So what we can do there is we can set a unbalanced protection. And so this is typically meant to protect for blown fuses, single phasing, things of that nature. Typically, this is an unbalanced current element. And give me just a second here. Okay, so it's an unbalanced current element. And we can set that with a relatively long time delay. Typically, we'll set that at around 10% negative sequence current, 10% of the positive sequence. So if we have negative sequence at 10% of the positive sequence, that could be a blown fuse upstream, something of that nature. If we have a downstream open circuit or an open conductor, we're going to have a lot more than 10%. We're probably going to have close to 30%. So we can catch those conditions again. If we have a single phase to ground fault, we may collapse that phase voltage. So if we have a fault elsewhere in the system, we need to set the time delay with the unbalanced protection long enough such that we don't misoperate for that condition. So typically you're looking around a few seconds for that time delay. Okay. So let's talk about ground fault protection. Of the faults that we'll discuss, and we'll talk about phase faults, we'll talk about differential protection, stator overcurrent protection, we'll talk about all those things. But the most likely fault that you'll have is a ground fault, right? So typically if you have enough voltage stress or mechanical fault or moisture in the stator insulation, you can get a ground, a phased ground. So if we look at this, I don't know if I can, let's see if I can do this. So if we look at this particular motor here, we can see that particular power system there, we can see that it's impedance grounded. So if this represents a transformer, this over here, if this represents a transformer, then, bear with me one second, if that represents a transformer, then that impedance on the transformer will limit the ground fault current, right? So a lot of the type of protection that we use will depend largely on the type of grounding. So with that said, before we proceed on, let's take the next pole. So the next pole basically is, the difference between neutral and ground is A, ground is measured and neutral is calculated. B, neutral is measured and ground is calculated. Or C, they are the same. Okay, and let's see if I can see the poll results as they're going on.
So far, everybody's gotten it right. Oops, I spoke too soon.
Oh, yep. Okay. Yeah,
We're
you
going the
didn't
wrong
speak.
way.
We're going the wrong way. Maybe when it was 100%, when it was 100%, maybe one person had voted, right?
Maybe.
So we'll go ahead and close the poll. It looks like 35%, 33% said they're the same. You can make that argument, right? We'll talk about how we make that argument in a few minutes. But according to the IEEE, and also according to the GE's relays, ground is a measured quantity.
Share your screen again, Terry.
Oh, I'm sorry. What am I doing wrong here? Sharing. Show screen. Okay. I haven't gone forward yet, but ground is, according to IEEE, ground is a measured quantity. Neutral is a calculated quantity. Right? So, and that's true of our relays. So what this looks like is neutral in GE relays is the vector sum of the three phases. So basically it is 3I0, 3 times zero sequence current. That's neutral. Ground in our relays is an input on the relay. So you can wire that input with a residual voltage connection. We'll talk about what that looks like here in a few minutes. Or you can wire a zero sequence CT to that ground input. Either way, it is an input on the relay, and that's what ground. So if you set a ground overcurrent on a Multilin relay, it is expecting something to be wired on that ground input. If you set a neutral overcurrent, it is going to operate from the neutral, the calculated neutral current. And John, in case I forget to talk about when and where they're the same, if I happen to wander into the next section, which will be phase over, or which will be differential protection, before I address when they're the same, interrupt me and tell me I forgot. Okay. So that said, let's move on. Right? Let's move on to another question. So the next poll question is the best ground protection system. The best ground protection system is A, zero sequence current CT, B, a residual ground current measurement, C, this neutral calculated measurement that I talked about, or D, it depends on the type of grounding system. So let's see what the poll says.
You really like these polls, I can tell.
I love these polls. They're awesome. Okay.
Y'all are doing good.
Yeah. I'll give you guys a hint. Anytime a fellow engineer asks you a question and one of the choices are it depends, begins with it depends, that's the right answer, right? Because we always, especially me, I always love these it depends type questions, right? And in this case, it does in fact depend on the type of grounding system, right? There are instances where zero sequence current CT is not that good of an idea, right? There are instances when residual ground current works fine, and there's instances when we should use neutral calculation. So it all depends, really, on what our grounding system looks like. So let's talk about what we use, what our grounding system looks like. Okay? So let's talk about the different types of ground CT connections. So one of the connections is, let's find my pen here. So this is a zero sequence CT, right? Now, what a zero sequence CT is it's a CT that basically encompasses all three phases, just like this CT is shown here. Now, what that means is that the magnetic field that's available to drive a flux into the core of that zero sequence CT is basically the vector sum of the magnetic field of those three phases. So if we have a single phase fault or something like that, we don't really need to worry that much about the CT saturated, right? Now, the other connection that we might use that I'll mention just briefly is this measured polarizer. This is this connection here. You don't see this very often on motor relays. You typically see this on a distance relay or some other directional type element. And this source that we show here, that represents a transformer. So we might measure the ground current on that transformer to directionalize, to polarize a directional overcurrent or distance element. Now, the other two mechanisms that we have are the neutral current. Remember, neutral is the calculated phases, right? So here's my three-phase inputs right here, J1 to J2, J3 to J4, J5 to J6. Those are my phase inputs. Now, if I want to operate a neutral overcurrent, that neutral overcurrent will be the vector sum of those three phases, right? Now, a residual connection looks like this guy down here. Now, this wiring that we show here, it's 4 and 869 relay. And so there's a ground input between J7 and J8 on the 869. And what we're doing here is we're basically, with this residual ground connection, we're basically doing the same calculation that the relay's doing mathematically here to get neutral current. We're doing that same calculation with wiring, right? Because what we have right here at this little dot is the vector sum of these three currents, right? So the difference that we have in those currents will be driven through this ground input, right? And if there is no difference, if those currents vectorially sum to zero, as they would in a perfectly balanced system with a perfectly built motor there, which doesn't exist in the real world, in that case, all the current stays inside the CT circuits, and none of it's available to be driven through this ground input. That's the key difference between the three different types, right? I mentioned those earlier. So the question then becomes, well, which one should I use, right? Because I said that it depends, right? And it does depend, but it depends on how your system's grounded. So let's talk about this zero sequence CT. Zero sequence CT, again, all three conductors pass through the zero sequence CT. All three conductors pass through that CT, and the magnetic field that's available to drive flux into that CT is just the vector sum of those three conductors' magnetic field. Simple. Now, there's a few things we should take into account here, right? So what happens if my transformer, so let's talk about how this motor might be protected. Let me find there it is. So let's say that sitting over here is a transformer, sitting over here is my motor, right? And let's say that transformer, it looks like, pretend that's the windings on the transformer. So that transformer, he looks like, it's solidly grounded. I'm having trouble drawing today. Sorry, guys. But let's pretend that transformer is solidly grounded. That's solidly grounded. My ground fault current, my available ground fault current, it might be depending on the impedance, the voltage level, all these different things, it might be 10,000 amps, right? It could be a lot of ground fault current. Well, most of these zero sequence CTs like we show here, most of those are like maybe 100 to 5, maybe 50 to 5. Well, if I try to pass 10,000 amps through a CT that's 50 to 5, I'm going to saturate that CT. So for this solidly grounded system, this zero sequence CT isn't necessarily a good protective solution. But if instead of that, I put some sort of, instead of grounding in that way, in a solidly grounded system, I have some sort of impedance there. So let's say I'm grounded like this, and I got a resistor there, and pretend that square there is a resistor, and then my ground's sitting down here like that. So if I'm grounded that way, I may limit my ground fault current to a much smaller quantity, right? So I could limit my ground fault current to a few hundred amps, 200 amps maybe. Or if this is in a generating station, I might have a high impedance grounded system where my ground fault current is 15 amps. Now, in both of those type systems, the zero sequence CT here is a better solution. The reason it's a better solution is because even if I get it at 50 to 5, I can sense down there in that lower range. I don't have to worry about CT saturation, those sort of things, right? So that's when and where I should use the zero sequence CT. So my next, let's see if I talk about, okay, my next type of ground input is this residual ground fault, or residual ground protection, right? So this is the wiring I show here. There's not a lot of difference between this residual connection, what we will see inside the relay, this residual connection, and a calculated neutral. So for that reason, rather than complicate my wiring, I would typically just use calculated neutral rather than this residual connection. It makes the wiring simple. Either way, I really like this sort of protection is appropriate for certain ground conditions. So let's go back to my two scenarios that I mentioned in the last slide. So the two scenarios I had was some sort of impedance grounded system and some sort of high impedance or solidly grounded system. So on that solidly grounded system, I couldn't really use my zero sequence CT because my fault current was 10,000 amps, right? Now, if my CTs here, they're 1,000 to 5, I'm 10 times CT, I might saturate some for this, for a downstream fault. But if I do, it's not that big a deal because it's a true fault that I need to trip. So this sort of connection is appropriate for that solidly grounded system. Now, what happens if I use this solidly grounded system, or if I use this residual connection for a high impedance grounded system, or an impedance grounded system, I should say. So let's say I limit my fault current to 200 amps, right? If I limit my fault current to 200 amps, then my CT ratio, as I said earlier, let's say that's 1,000 to 5 CTs. Well, I could have 10% unbalance on, or not 10%, well, I could have 10% unbalance, but I could have 10% inaccuracies in my CTs based on the C37 standards that CTs are built by. So basically, I guess I should say C57, but C57, C37 standards that describe these CTs basically say that during the linear portion of its curve, it produces 90% accuracy. Well, that means it could have up to a 10% inaccuracy. Well, 10% of that 10,000 amps is 100 amps. So I would have to set, so I could have 10% inaccuracy, which might look like, if I ignore the fact that this is vector emission, 100 amps of unbalance just because of CT inaccuracy. That means I'd have to set my ground fault current pickup greater than 100 amps to prevent misoperation. And if I'm going to set it greater than 100 amps, that means I only get to protect 50% of my stator insulation from a ground fault current. So that's a problem. I cannot set that low enough to provide the protection I need. So for that reason, this sort of protection, or this sort of ground protection, isn't really appropriate for a impedance grounded system or high impedance grounded system. Now, there are some impedance grounded systems that limit fault current to 1,000, 2,000 amps. That, whether or not this sort of ground will be appropriately for that 1,000 or 2,000 amps of ground fault current will depend largely on the size of these CTs up here, right? If the CTs are really, really big, then I may not be able to get down there low enough. Okay, so with that said, let's talk about phase fault protection. So,
Terry,
as I said earlier,
you forgot to say when they're the same.
What'd you say? Oh, yes. When are they the same? When are they the same? So the same is that, what was my poll question again?
Neutral and ground.
Okay, when are they the same? They are the same in this sort of connection that we show right there. So in that sort of connection, they are the same essentially, because the calculated, we're either going to calculate this with the wiring like we are here with, let's see, let's go back to this slide and let's erase some of this stuff. Yep. They're the same here because the calculated quantity, whether we're doing vector calculations inside of the relay or whether we're doing it with this wiring connection, they're basically going to be the same. So again, that's why I sort of like to do a neutral overcurrent when I have that solidly grounded system, and rather than complicate my wiring and having to wire the ground into it. Thank you, John. You did exactly like I asked you to do. All right. A few more years, I might have you trained. Okay, so the most likely fault we're going to have is a ground fault. But we still have to protect for phase-to-phase faults. Those are rare in these sort of machines. Motors, generators, even transformers, phase-to-phase faults are rare. Now, the reason phase-to-phase faults are rare is because we do everything that we can to prevent us from having a phase-to-phase fault. And so what I mean by everything we can is we keep the phases separated inside of the machine. We might use isophase bus. There's lots of air between the phases. There's just, that sort of small insulator between a phase and ground. So that makes a phase-to-phase fault less likely. The reason we do all that is because a phase-to-phase fault typically provides a whole lot more fault current, which means a whole lot more damage than a phase-to-ground fault. And so since it is so much more damaging, we want to make sure that we protect for that, and we get that off of our system as fast as possible. Now, one of the ways that we can do that for really large motors that we want to protect very well is with a differential. Now I'm going to jump through some of these slides here. Bear with me because I have them out of order. But there are two ways to do differential. And this is the better of the two ways. And the reason I say the better of the two ways is because the challenge with all differential is not getting it to operate for a fault. The challenge with all differential is keeping it from operating for a through fault or a problem elsewhere on the system. Now, the real challenge there because of that is the CTs. Now, I mentioned earlier that CTs only provided about 90% accuracy in the linear portion of their curve. Now, what we're doing with differential protection is in all differential protection, we're going to measure the current flowing into the zone of protection and the current flowing out of the zone of protection. The vector sum of that current flowing into the zone of protection and the current flowing out of the zone of protection should be zero. We have a fault, that's not zero, we should operate. So that's what differential is. The problem is we have these inherently imperfect devices of CTs that don't particularly provide us enough accuracy always. And the real challenge we have is with CT saturation. So this type of CT, or this type of protection here, it's called a core balance CT. And it works in a similar way to the zero sequence CTs that I mentioned earlier, in that we take the current flowing into the motor terminals and the current that's flowing out of the motor from the neutral end. And one of them goes through the CT. So one of the currents goes through this direction, and the other one will go in that direction. So that's A phase that we're looking at right here. And works like the zero sequence CT in that the magnetic flux the magnetic flux that's available to excite the core is the vector sum of those two currents. And those two should be zero. So unless we have a fault, we should not see current in the secondary to the CT. So this lets us set this very sensitive. Now we can also do some things in the motor to desensitize it during starting. This particular CT, or this particular CT arrangement, we don't really have to. Okay. The other way that we can do this is with a differential summation method, or we can either sum this as it's shown here outside of the motor relay, or we can sum it inside of the motor relay. Now, this is not a very good way of doing this because what we see coming into the relay here is just the vector sum of these two currents. So you can imagine if this CT saturates here, but this CT over here performs perfectly for some reason, then we would see current down here. And so for that reason, this isn't the best way to do this. The better way actually is the first wiring that I showed, but the other way is this sort of current input, where we wire all the currents individually to the relay. Now, the downside to this sort of arrangement is that it requires an extra set of CTs, right? So it requires a set of CTs on the terminal side and the neutral side. Now, when we compare that to the core balance mechanism that I showed a few slides earlier, that still required the same number of CTs. It still requires 6 CTs because you've got one CT that that is on the terminal side. You'd use that for your overcurrent protection. You'd use that for your thermal model. And then the core balance CT is another input into the relay. It's also another CT. On this particular mechanism here, you're again using 6 CTs. The ones on the terminal you'd use for the motor thermal model, your overcurrent protection. The neutral side CTs are just going to be used with this differential. Now, the only nice thing about this one is you don't have to route your cables from the neutral side to the terminal side, right? So the core balance mechanism, those CTs really have to be installed by the motor manufacturer. You could install these after the fact, this sort of arrangement, but I've never really seen this. Typically, these CTs are provided by the motor manufacturer. Okay? All right. Before we jump on, let's do another poll. Keep everybody awake. So, the poll question is, you should set your phase IOC to just above full load current of the motor. True or false? So let's see what the poll says.
Terry, you want to answer a question while the poll's going on?
Sure.
How does this affect cabling the motor? You had the dual set of CTs.
How does what now?
How does this affect cabling the motor with that differential set of CTs?
Okay, so typically it doesn't affect the cabling of the motor because the CT, I guess it depends, right? It depends on where your CTs are located at, right? So typically your CTs for your one side will be at the contactor.
Correct.
And so you're just running cable from the contactor to the motor terminal box. The CTs that would be provided for the differential, either as a core balance CT or as the neutral side CTs, they would typically be in the motor terminal box, typically provided by the motor manufacturer. So your cabling for power for the motor, not really affected. Cabling for wiring those CTs, yeah, you're going to have to wire those CTs and route those back to your protective relay. Okay, so it looks like 76% said that you can't set this just above full load amps. And the other 24% probably got this right, but you took a more liberal interpretation of just above full load amps, right? So there's a problem with motors. There's a problem with motors in that when I try to start this motor, I'm starting it across the line and it's an induction motor, I'm going to draw maybe 6.5 times full load amps just to start the motor under lock rotor conditions. So when I do that, I've got problems, right? So the problem I've got is I may trip if I just set the overcurrent a little bit above full load amps. I'm going to trip every time I start the motor. Never going to successfully get this thing started. That's a problem. So I'm going to have to do something a little bit different. So let's see. Here we go. You guys are viewing my screen now. So what I typically want to do is I want to set the overcurrent element large enough to accommodate not only that locked rotor current, but also enough for that I don't misoperate because of the DC offset. So you can see what I show here. When we first start that motor, depending on where we start, where we start at on the voltage waveform, we're going to have some offset, some DC offset on the current waveforms. That can cause some calculation errors in any microprocessor-based device. So because of that, we want some additional accommodation for that. So typically, blocked overcurrents is 6 to 6.5 times full load amps. And so I want to set it to 1.7 times that at maximum started. So that's 1.7 times 6 times full load amps. And that's where I want to set my overcurrents to protect the motor for a phase-to-phase fault. Now, there's a caveat that I should put here too. Yeah, I'm getting an echo, John or somebody. There, it's gone now. That's great. So the caveat is that, that's how I want to set it. I want to set it at 1.7 times 6.5 times full load amps. The caveat that I want to warn you about is that you may not want to use an overcurrent element, a phase overcurrent element, if you have a contactor. If we think about what a contactor circuit looks like, there's my pen. A contactor circuit looks like this. There's this thing here, right? There's some sort of elaborate control. There's a contactor, and then I've got my motor, right? This thing that's right here is a fuse. And that fuse is really meant to protect the motor for phase-to-phase faults. So that contactor may not, I mentioned earlier that, if we have, if we have an impedance grounded system, we may be limiting ground fault current to 400 amps, but our phase fault current might be 10,000, might be higher than that. The contactor really isn't meant to break fault current. A breaker breaks fault current. The contactor is meant to start and stop the motor. Now, we want to use the contactor for ground fault protection, typically because the ground fault current is typically less than the available ground fault current is less than the contactor interrupter rate. We want to check that, make certain of that. But for phase faults, we also want to check and make certain that we're not trying to open that contactor for a phase fault. If we do, we may open that contactor once, right? Okay, John and Mike, they sell motor control centers. I'm almost certain of it. We would prefer that fuse to blow though, so that we don't destroy the contactor. Okay, and then the last thing that I really want to talk about is we probably also want to use some stator RTD trips. So we can use some stator RTD trips. I mentioned last time that we could use Unbalanced, or we could still use stator RTD biasing of the thermal model. We could also trip from those RTDs. Also, we could trip if we could have embedded RTDs in the bearings, and we could trip those as well. Now, with that said, let's talk about, in the last few minutes I've got before I address questions, the family of relays that GE offers to protect motors. So on the low end for low voltage motors, we have the MM200 and MM300. These are targeted to low voltage motors, 480 volt, maybe even 120 volt. And then a very cost-effective solution for the low end, and if we imagine this, I would say that, where's my pen? There's my pen. So if we went along that axis is price, and along this axis is functionality. So if we just need to protect the motor, a 339, if we just need to do motor thermal model, ground fault protection, some basic functions, a 339 is a very cost-effective way to do that. Next up on the model is the 369. 369 has been around a long time. It's still around. What you don't see on this list is the 469 anymore. You don't see the 269. Now, the 269 has been obsoleted. I don't show the 469 on this this graphic because obsolescence plans have been announced for the SRs. So the 469 is an SR relay, 745, 750s, 469s. I think it was a couple of years ago we announced the obsolescence plans and the last time buy window for those SRs. And so the SRs, that's the 469, they will be, the last time buy window is at the end of this year. 369, it's still around. 369 is still around. No obsolescence plans have been announced as of yet. The 869 is what the replacement to the 469 would be, and the 869 is a much more modern relay. It's draw-out construction, less like the 469. So it's got a really nice screen on it. It can do differential protection. Most of the settings and most of the settings that I showed, and most of the drawings that I showed in this presentation were from the 869 relay. And so with that said, I think I left a few minutes to address any questions that can come up. So, John, is there a way for me to see any of the questions? Oh, wait. There's a question.
Polls.
We got another poll?
I got 2 more polls.
Oh, did I list? Okay, well, let's do the polls. Were these polls that I provided?
No.
Oh, okay.
This first poll is, would you like someone to contact you regarding the motor protection? And while we're answering the polls, see if questions come in, then we can discuss them. So we're multitasking, Terry.
Okay. Okay. Let's see.
You can pull the question.
Said yes. Well,
you can pull up the questions.
Okay. Yeah, the only one I'm only seeing this one that was asking about the motor cabling.
Correct.
Is there
no
more?
question. I don't see any other questions
either. Okay.
Yep. Surprised nobody has any questions.
We may be talking to an empty room.
We could, but no, we've still got a lot of people signed up and going. All right, I'm going to close this poll. And 20% of you wanted me to give you a call. So we will take care of that. And the last poll, which Terry cannot vote on, is we just want everybody to rate your presentation 1 to 5.
Oh, could I vote on any of the others?
No, you couldn't. We don't let you vote.
Oh, okay.
I know you give yourself a 6 on this.
Yeah.
If you want a copy of the presentation, it's already on our website in the resources tab. You also can grab the handout, which has got a copy of it. I will have this recording of the video also on the website. All our past videos and presentations are on our resource tab. So we've already got that for you too. All right. Oh, here we go. We got a couple questions, Terry. Do you see the questions, or do you want me to read them to you?
Well, let's see if I can see them.
Go to the questions. You can
How do you integrate motor RTDs into these motor protection schemes? So it depends, right? So what it depends on is whether it's a stator RTD or a bearing RTD. One of the things that in my haste to finish on time that I didn't mention was that if we're going to use RTDs, we should use RTD voting. So the 869 supports RTD voting. And what RTD voting is, it says, hey, you got to have this RTD at a high value and this RTD at a high value before you would trip, right? So if we're going to trip, we want to do RTD voting. Part of the reason for that is that RTDs can fail. A lot of times if they fail in a high temperature condition. So in other words, they're saying, hey, there's a high temperature. So we would integrate RTDs into motor protection. Typically with stator RTDs, we would do RTD biasing, and then we could detect a bearing problem with a bearing RTD trip. We could also do stator RTD trips. If we do that, we want to set that, just right at the stator insulation class. Okay, and you said there's another one.
You see the next question?
When setting the overvoltage and undervoltage, is it always versus the normal 4160 volts? So the way I would address that is, it is always versus the several things, right? It is always versus the motor nameplate, right? So if the motor nameplate says 4160, if the motor nameplate says 4160, then yeah, you'd set that undervoltage at a 10% overvoltage or a 90% undervoltage. Now, one of the things that you should take care about is the way that you set your VTs, right? So a lot of times what you will have on your VT settings, I shouldn't say a lot of times. On VT settings, on Multilin relays, what you have is you have a ratio and the secondary voltage, right? So the ratio should be the ratio of the VT, and that's what you should set it to. The secondary voltage should be what you see on that relay under nominal conditions, right? So if you're going to have whatever the ratio is to 4160,
35 to 1.
Then 35 to 1, and what would that be on the secondary?
200 to 120. So at 4160, you're getting maybe 118, say.
Yeah, 118. So you'd set that to 118, and then if you wanted to set overvoltage, then you would set overvoltage at 1.1 per unit.
But your motor may be a 4,000 horsepower rated motor on your 4160 volt system, so you're already overloading it, correct?
Yep. Yeah, you can. And unfortunately, because of my internet problems today, I've moved up to my back porch, and my office is downstairs, and that's where my calculator is. That's why I'm struggling with all these numbers that John had to help me with. John didn't have these memorized. He's got a calculator.
All right, next, can you wire in a remote reset for the 469 or 869? Calvin Hill asked that, and the answer is absolutely. You can remote reset them.
Yeah.
With an input or virtual a lot of ways. You want to read the next one, Terry?
Oh, there's another one.
It's 4 more.
Okay. I got to figure out how to do this better.
You can drag it over into your screen and see it if you want.
Okay. Would the CTs be smaller for the application where the phase wires go in and out of the CT? So that is the core balance CTs. Yes, they would be smaller, right? So if you've got 1,000 amps, full load amps on the motor, your terminal CTs probably are going to be around 1,000 amps. If you do this summation method of differential, then the neutral side CTs, they need to be around 1,000 amps also. If you're doing a core balance CT, then it has to be 1,000 amps because you're only going to measure the current going on either side. So it doesn't have to be 1,000 amps. Not only does it not have to be 1,000 amps, you may have a C50 or C200, who knows, some higher C rating on those phase CTs. Since your core balance CTs are only measuring the difference, then they can be a much smaller accuracy class. Since they're a much smaller accuracy class, they can have less iron, which gives them less real estate. Okay.
Next question from Mr. Rollinger is words in the specification. Marty, I've got guideline specs that I could send you on all these relays. So, and we have a
Yeah.
program called Launchpad. For those that don't have it and want it, let me know. It's a great program, shell product. You can download and get information instead of having to go to the Multilin website.
Yeah.
Next
I'd
question.
say that the words for the specification are shall be GE Multilin.
I like that.
Yeah. Yeah. And period. There's a period at the end of that sentence. There's
What
no transition like a or, right? What takes a priority, relay thermal model or voted winding RTDs? So I think the question there is what should take priority in tripping. I think
we actually use both.
yeah, you're actually. I mean, it isn't like you're giving one of the higher priority or the other. They're both equally able to trip.
And we actually use them together. So we've got an RTD function called RTD biasing, where we actually look at the RTDs and the current together to actually determine when we trip. And Terry's got some great case studies on that, where people set relays wrong and couldn't get it started.
Yeah. Yeah. Are the SKM library models available for these relays? Yes, as far as I know, I think that the 8 series is in the SKM library, or library, depending on your pronunciation. But yes, I think the 8 series is in there. I'm pretty sure that the others are as well. One of the bigger question that I often get asked around the SKM libraries is how do you do things like differential? How do you do differential, especially for like a bus differential or even a motor differential? And like if you're doing a differential, there is on any of the, especially if you're doing this for a arc flash study, and you're using the differential to shorten your tripping time to reduce your arc flash incident energy, the way you do that is you enter a definite clearing time. So SKM, arc flash, everybody has the ability to enter a definite clearing time. So you'd look in the manual, you'd say, okay, I'm using a B90 for bus protection. That has an operate time of 1 cycle, and I have a 3-cycle breaker on the other side of that. So I put a definite clearing time of 4 cycles, and that's how I do that. But yeah, for the overcurrents, those things, they're in the SKM library.